Japan constructs skyscrapers at a pace of 3 to 4 days per floor, outpacing the United States' average of 6 to 8 days and rivaling China's ability to complete entire high-rises in just 15 days. This speed advantage emerges from an unlikely source, a severe demographic crisis where the average construction worker is 54 years old, with nearly a third over 60. Faced with a shrinking labor force, Japanese engineers have pioneered a solution that eliminates the traditional construction site entirely. Instead, they deploy a self-climbing, fully automated factory that ascends the building, turning vertical construction into a precise robotic assembly line. This is the story of how Japan is redefining urban development through robotic integration. For decades, building a skyscraper followed a predictable, laborious rhythm. It's a sequential dance of steel and concrete, where each step must wait for the last to finish. First, the steel skeleton rises, piece by heavy piece, lifted by a tower crane that becomes the project's heartbeat and its primary bottleneck. Then come the concrete floors, poured one level at a time. After that, crews install the curtain wall, the mechanical systems, and the interior finishes. This stop-and-start process is incredibly human-intensive. For a 50-story tower, the timeline stretches to 3, even 5 years. The pace is dictated by the crane's capacity and the safety of workers performing delicate tasks hundreds of meters in the air. Every bolt tightened, every weld made, depends on human hands working in precarious conditions. This method worked when labor was plentiful, but Japan's aging population has made it unsustainable. The industry faces a simple, stark equation: more complexity plus fewer workers equals a full-blown construction crisis. The old way of building up was no longer a viable path forward. Across the Pacific, American engineers tackled the same problem of efficiency, but from a different angle. The U.S. approach to high-rise automation focused heavily on prefabrication, building components off-site in controlled factory environments. Take the Salesforce Tower in San Francisco, a 61-story landmark completed in just 4 years. Its success was built on advanced prefab techniques. Entire bathroom pods, complete with tiles and fixtures, were manufactured miles away and trucked to the site. Massive facade panels and complex mechanical system modules were assembled in factories, then slotted into place like giant Lego bricks. This method significantly reduced on-site labor and improved quality control. The statistics show the gains. For steel structures, the U.S. averages a floor cycle of 6 to 8 days. The approach also has safety benefits, with the U.S. Bureau of Labor Statistics reporting a construction fatality rate of 10.2 per 100,000 workers in 2022. But this American innovation has a fundamental limit. While it perfects the components, it still relies on the same traditional crane-based system for final assembly. The site itself remains a chaotic orchestra of coordinated lifts, with the crane as the solitary conductor. The process is more efficient, but the core assembly methodology, building upward from the ground, remains unchanged. It's an upgrade to the traditional model, not a reinvention of it. While the US optimized the parts, Japanese engineers reimagined the entire process. They asked a fundamentally different question. What if the factory came to the building instead of the building coming from the factory? The answer is Obayashi Corporation's Smart Construction System, a paradigm shift that transforms the construction site into a single, towering, automated assembly line. The core innovation is a self-climbing robotic platform that encases the top several floors of the rising structure. This system doesn't just assist workers, it becomes the primary builder. Imagine a colossal, multi-story factory that can lift itself, using hydraulic jacks to climb the building's core at a precise, relentless pace. This eliminates the single greatest constraint, the stationary tower crane. With the building now encased in this automated shell, multiple trades can work simultaneously instead of sequentially. While robotic arms on one level are placing and tying rebar with millimeter precision, automated concrete placers on the floor above are pouring slabs. Simultaneously, on another level, welding robots are securing steel frames, and automated installers are placing prefabricated facade panels. This is concurrent construction, a concept previously thought impossible in high-rise development. The entire operation is choreographed by a digital twin, a perfect virtual replica of the building in its building information modeling system. This allows for real-time adjustments and ensures every component, from the largest beam to the smallest conduit, aligns perfectly before it's ever installed. The results from projects like Tokyo's Toranomon Hills Business Tower are staggering. Where traditional methods might take weeks per floor, this automated system achieves a floor cycle of just 3 to 4 days. According to Obayashi's 2021 report, this approach requires 30% fewer on-site workers while maintaining and often increasing overall output. But perhaps the most dramatic impact is on safety. At these automated sites, falls from height incidents, one of construction's most persistent dangers, have been reduced by an incredible 80%. This isn't just a faster way to build, it's a fundamentally safer and more precise industrial process, unfolding silently hundreds of meters above the city. So how does this self-climbing factory actually function? The mechanical heart of the system is the hydraulic climbing mechanism. Massive jacks, integrated into the platform's steel frame, grip the building's reinforced concrete core. After a floor is completed, these jacks extend, lifting the entire multi-story platform, which can weigh thousands of tons, by a precise increment, typically 1 floor height. The process is guided by a network of laser sensors that provide real-time feedback, ensuring the platform remains perfectly level and aligned throughout the climb. It's a ballet of immense force and near-microscopic precision. This robotic platform is a self-contained ecosystem. It carries its own power supply, often a combination of generators and temporary electrical feeds, and features an integrated material handling system. Instead of waiting for a crane to lift materials from the ground, components are delivered to the top of the building via high-speed, automated construction elevators that are synchronized with the climbing rhythm. Robotic arms and automated guided vehicles then distribute steel beams, rebar cages, and pre-mixed concrete to the exact location needed on the working deck. Quality control is continuous. An array of sensors embedded throughout the platform monitors everything from the viscosity of the concrete as it's poured to the torque applied to every structural bolt. This data feeds back into the digital twin, creating a live, as-built model that can flag any deviation from the design specifications instantly. This system is also remarkably resilient. It's engineered to operate in conditions that would shut down a traditional site, including high winds and rain, protected by the temporary enclosure the platform itself provides. A prime example of this system's capabilities was demonstrated during the construction of Tokyo's Nihonbashi Onchome project. The climbing system maintained a steady pace even through seasonal typhoon conditions, something that would have caused weeks of delays with conventional cranes. The technical specifications are staggering. These platforms can handle loads exceeding several hundred tons, climb at a rate of several meters per hour, and maintain positional tolerances within just a few millimeters across a footprint the size of a city block. This isn't just construction equipment, it's a portable, vertical factory with the precision of a semiconductor plant. The impact of this robotic revolution extends far beyond just faster completion dates. The economic implications are profound. By slashing construction timelines from years to months, developers see massive reductions in financing costs, the interest accruing on loans for a project that now takes 2 years instead of 4. This fundamentally changes the financial calculus of building tall, making ambitious projects more viable. The environmental benefits are equally significant. Building with robotic precision leads to a dramatic reduction in waste. Traditional construction sites generate mountains of discarded materials from errors, over-ordering, and damage. The automated system's precision, guided by the digital twin, optimizes material usage down to the last kilogram of steel and cubic meter of concrete. Obayashi reports a 25% reduction in construction waste on automated projects. Furthermore, with most materials delivered via a coordinated, just-in-time logistics system directly to the climbing platform, the constant coming and going of heavy trucks is significantly reduced, cutting down on local emissions and traffic disruption. Perhaps the most transformative effect is on the workforce itself. The role of the construction worker is evolving from manual labor to technology supervision. Instead of physically tying rebar or wrestling with heavy formwork, workers on these sites are trained as system operators, robotics technicians, and data analysts. They monitor control panels, perform maintenance on the automated equipment, and interpret the real-time sensor data flowing from the digital twin. This isn't about replacing humans with machines. It's about elevating human work to a higher level of skill and safety. The dangerous, repetitive tasks are handled by robotics, freeing people to focus on supervision, problem-solving, and quality assurance. This shift has profound implications for urban planning. When cities can add vertical density much more quickly, it eases pressure on urban sprawl and enables more efficient use of infrastructure. The technology also has significant export potential. Japanese construction firms are now positioning this integrated, automated system as a global commodity, a solution for other densely populated nations facing similar labor shortages. Of course, this raises questions about technological unemployment, but the industry's argument is that the demographic reality makes this transition necessary. The choice isn't between humans and robots, it's between building with robots or not building at all. The human element is being redefined, not eliminated, creating a safer, more technologically advanced and sustainable future for the construction industry. This Japanese model of automated construction isn't staying within its borders. Southeast Asian nations, facing similar urban density and labor challenges, are rapidly adopting these technologies. However, global adoption faces significant cultural and regulatory hurdles. Different safety standards, union traditions, and building codes present barriers that the technology must adapt to overcome. This stands in contrast to places like China, which prioritizes mass, rapid construction, often with vast human labor forces, rather than this focus on precision automation. European firms are exploring hybrid models, but Japan's fully integrated system represents the most significant leap forward. This innovation is creating a feedback loop where the very possibility of automated construction is now influencing architectural design, with new skyscrapers being designed from the ground up to be built by robots. The automated construction sector is projected to grow into a $15.5 billion global market by 2027. Japan's self-climbing robotic factories represent a paradigm shift in high-rise construction, positioning the nation at the forefront of a global competition for building dominance. This approach contrasts sharply with China's methodology, which relies on massive human labor forces to achieve rapid construction speeds, completing skyscrapers in as little as 15 days through government-driven, labor-intensive projects. Similarly, the United States has optimized efficiency through advanced prefabrication, building components off-site for swift assembly. Each model reflects distinct priorities. Japan's precision automation addresses demographic decline, China's scale meets urgent urbanization needs, and America's modularity enhances safety and quality. As urban populations swell, the critical question remains: which of these approaches, robotic integration, mass labor, or prefab efficiency, will ultimately define the future of city skylines? The answer will shape construction methodologies for generations.